Welcome. This is an honor to talk with Dr. Dibyendu, our long-time collaborator and mentor, and nice to be introduced by Professor Govind as well. So I broadly going to talk about DL4 compilers, turbocharging compilers, optimization for deep learning. So a lot of material to be covered. I mean, unfortunately, it's the last talk of today. Everyone is tired, but please hold on. It's going to become mathy and a lot of concepts, but it's going to be fun. Okay, so first of all, this was possible only because of various contributors and from various things. Our PhD students, Venkatakirti, Siddharth Jain are here. Our graduated PhD students, Shalini, Rohit, of course, and various bunch of MTech students from IIT Hyderabad. And our acknowledgements due to Professor YNS, Professor Albert Cohen, and a whole bunch of others, and of course, Sandhya Mannar Swami and Kumar Venkatraman and a whole bunch of others. So this is the joint work with many co-authors. So that's why we are here. Okay. So it's well known that compile optimizations are fundamental for performance, and the talk is about how to make real help in that. So for various scaling the optimizations for various hardware languages and frameworks has become very difficult task, and they in general do not have polynomial time solution. This is well known. For example, NP completeness is any interesting problem is either NP hard or undecidable in compiler entire framework. So in general, you have hundreds of variables, and then you have building compilers is really a job for life. You sign up for compilers right now, you are in for life. So how do we go forward? So, for example, you have these manual and well-trained heuristics in well-established compilers like GCC, LLVM, of course, and they guarantee correctness. And they are come with, literally speaking, hundreds of man years. This is probably even more. So how to put DL into that, DL or for example ML algorithms into that, and then how to ensure that we get optimal performance while at the same time how to ensure correctness. That's the main thing. So I mean, typically you can assume that you can collect examples, learn for examples, and update heuristic. This is iterative process. But the problem here is that model is model is itself the heuristic. So you can have various new program features, and then this is what we call the feature-based learning. This has been used for some time. This has been used by various groups in the world where features are learned, where features are well decided a priori, and then from there the features are used to decide the optimization. That's okay. But overall framework which we want to put in is approximately the following. There's a slide missing here. Okay, okay, yeah. So what we want to do is that you begin from a compiler optimization. You want to decide on the representation of the program. Representation of the program, it could be, for example, lexical tokens, abstract syntax tree, and intermediate representation at various levels. And what happens is that you have to convert this particular intermediate representation into a high dimensional vector space. For example, whatever it is, because that's the language which the machine learning algorithms understand. They understand high dimensional vector spaces. So that's the thing. So for that, you can choose the embedding, and the path which we have chosen is something called representation learning based. Please pardon me because somehow one slide got disappeared, but I'm trying to make it up. So the question here is that there are broadly two ways of going into high dimensional space. Many research groups, they have also tried. For example, using feature selection, carefully, manually selected features. For example, number of basic blocks, number of for loops, all kinds of techniques, all kinds of number of paths, etc. These can be carefully fed, and then you can learn. You can train, and then from there you can use it to drive your optimization. But the current, but we can also propose we can also go into the alternate direction called something called representation learning. Representation learning, when the expert compiler will not have to feed these features. Because you go into, for example, there is a branch of machine learning called representation learning, and then we'll get into it in a minute. So in that space, for example, you put into, I'll get into representation learning in a little while, but the moment you get this embedding, then you can use it for many purposes. You can use decision trees. You can use, for example, any machine learning model. You can use LSTMs, all kinds of fully connected layers, as well as transformers, whatever. So, and then you can use it for various applications in the sense of various optimizations. For example, it can be rationalization, it can be some kind of phase ordering, or it can also be distribution. This is the distribution, this is the phase ordering, as well as the rationalization. So you can construct the embedding, and then you can learn it in a careful manner, and then you can use it for various optimizations. Is the main premise of large part of this talk. So the moment you're talking about this is kind of okay. Here, the moment you talk about program representations for ML, it's well known. It's well known. For example, NLP folks will look at WEC, GLOW, etc., and image processing people will talk about CNN, AlexNet, etc. What is the equivalent for this from program analysis, from program perspective? Let's actually carefully understand what good program embedding. First of all, it should be independent of the source language and architecture. This is good. It's important to be independent of both of these, and it should capture both syntax and semantic features of the program. And for example, it should have diverse applications. For example, you want to create an embedding, you may want to use it for optimizations, but you may also want to do for software engineering applications. For example, program similarity, all kinds of pattern matching, replacing the codes with a high performant code, binary version, that kind of thing as well. And it should be scalable as well. Scalable means it should have faster training time, and it should be lightweight. It should use lightweight ML models, and in general, it should not use out of vocabulary. For example, out of vocabulary is a very difficult thing which we want to avoid, because machine learning in general can predict only what it has seen, and avoiding it seems to be an important problem here. So that's how we want to define a good program embedding. And this is work. This is IR2. Then comes in the IR2WEC. IR2WEC is, as you can see the name, it takes intermediate representation, primarily LLVM intermediate representation, and converts into a vector. And it's primarily LLVM IR based, and it's a language and machine independent program analysis based approach. And it's what is called distributed encoding. This distributed has nothing to do with parallelism. It kind of has to do with the information being scattered across all the vector. For example, the moment you converge on something called a feature vector, this dimension is for this, while this dimension is for this. That's number of basic blocks, number of loops, whatever, that kind of thing. On the other hand, distributed encoding distributes the information across all entire thing. And it's a bottom-up approach, and it actually, there's a beauty in it, and it doesn't need any complex ML models, and it turns out that it's independent of applications as well. So this IR2WEC, we are going to cover IR2WEC right now, and then we are going to talk about various applications of it in compiler optimizations, and a couple of variations as well. For example, when you go to backend, our group has also proposed something called MLIR that is very particularly used for rationalization. So there are vanilla versions of this. So we'll cover that as well. So the moment you're talking about intermediate representation, this is the classic LLVM infrastructure. You have the front end, you have the optimizer and back end, and then, as you well know, this is front end is language specific, and the back end is architecture specific, and then in between you have the LLVM IR, which is both kind of architecture and machine independent. So in a similar manner, IR2WEC The classic IR2 also is in a similar manner. It's a initial representation. It takes the LLVM IR and it takes the tuples from the instruction. For example, here you have you have a store I32, and then you get a bunch of tuples out of it. You get triples out of it, and then you have a store type of integer type, as well as all of these. For example, this store maps to this opcode, and so on and so forth. And then this is fed into a a framework called trans-E that takes that takes a triple. This particular triple, it takes a H plus R. It takes 3 vectors and then tries to map tries to respect the H plus R is equal to T. That's the main point of it. And on training, what happens is that you get something called a seed embedding vocabulary. This seed embedding vocabulary is not very clear, but what we want to understand is that there is a integer types are segregated, and then all kinds of types are encapsulated in this. From here, you can use you can use this particular seed embedding vocabulary to get the embedding of the input program. This particular input program that will actually take the opcode weight as well as the type weight, and then all these arguments, and then gives a weighted function. Please understand this. This is a n-dimensional vector. This is an n-dimensional vector. This is an n-dimensional vector, and then this particular weight vector is the n-dimensional representation of just this particular instruction. And this happens to all the entities of the input program. Just like LLVM IR, you have modular representation of LLVM IR. You have instruction, basic block, loops, functions, modules, etc., etc. This iteratively happens for all the entities of the input program. So the moment you get this, I mean, as of now, in the published version of IR2 these W0, W2 are some heuristic, but there are extensions are also possible. This is some cute thing which we did. So now that you obtained the embedding for the particular each of these entities, you can actually propagate it in a nice manner as well. So there are some data flow analysis enthusiasts here. So actually you can create nice equations for the data flow propagation. But this is not the classic Professor Khetkar kind of data flow analysis framework. This is the data flow equations on the embedding space. This is something which we want to understand, because that double square bracket, it's actually n-dimensional vector. So I think you can actually create this particular, this is the instruction. Here is the instruction. And then you have some kind of loop and if then else, etc. And then this embedding of this particular vector I2 is WO plus of times the LOCAS embedding plus WT, which is times the embedding of the integer type. Okay, that's good for this particular instruction. And similarly for this particular I4, I4 is you can see that it depends on this guy as well as this guy. You can have W0 of load plus WT, which is the weight vector given to the type, as well as something to the pointer type, plus WA of I2 plus I3 plus I9, I2 plus I3 plus I9. Okay, this is kind of cute. Now the moment you add it up in this manner, then I mean so on and so forth, you construct these embeddings like this in the embedding space. This kind of data flow analysis propagates, and here you are. Okay, you can actually, it's pretty beautiful to see that you can actually define data flow analysis equations in the embedding space itself. It's very heartening. And then you can actually coalesce, how you can actually collect the information in a nice manner using the standard live variables, scalable variables kind of thing. For example, you have the basic block. Embedding is just the live of all the individual instructions. And similar for a function, it's the collaboration of the vectors for the basic block. And for a program, it's the data flow equation of all the functions in the program. So this is this happens, and this is what we constructed. And then the moment you construct embedding, you can do a lot of stuff. You can really do a lot of stuff. You can do what you can do, for example, software engineering as well as compiler optimizations, ERWin compilers. So we can do rationalization, for example. We are going to talk about this. It's a classic NP hard problem. It's been approximated by different heuristics, one of the hardest problems ever. We can do some frequency scaling for energy optimizations, etc. And then you can do algorithmic recognition and binary similarity. And you can also do compiler phase ordering, which is well known to be NP hard because too many permutations. So you can do a lot more. You can do a lot more. For example, in this talk, before we get to it, I think we'll talk about this. This embedding itself is worthwhile studying. For example, when you train with something like spec benchmarks, whole benchmarks, spec benchmarks, it's interesting to note that the embeddings have they start living their own life. What happens is that all these multiplication divisions they are coalesced together, while the standard constant variable etc. function pointer they are clustered together, and so on and so forth. It's kind of also nice to see that the division operators are coalesced together. They cluster together, and then some other operators they cluster together. This is something beautiful. This happens for this, and not just that. You can also use this for various analogies as well. For example, you can use this particular thing for the to answer questions like, for example, you have you can have addition versus multiplication, shift left or shift right. You can all these shift left and shift right. They are learned in a nice manner. Okay, so this is taken from Professor Aaron Yahav's talk. This particular kind of putting together all the various models. So their earlier works, for example, there was a deep tune by Edinburgh team, and then there was code NN, and then code to seek, etc. So as you can see, you can have various levels of abstraction from the program. You can have lexical tokens, you can have abstract syntax trees, interpreter penetration, and program analysis info. And for example, in particular, IR2A comes here. It has very less number of, pretty less number of amount of learning effort, while at the same time, it uses the interpreter penetration and program analysis info. Broadly, it uses the IR, it builds from the IR, and it also uses these data flow equations and other fancy stuff. That's good. So with that, our students they begin to conquer the world. So you have these ML-driven optimizations. You can use it for various things. In the last couple of years itself, there are at least 200 papers that try to build ML optimizations in recent years. The important fact to understand here is that it's a need of the hour is how to build compile ML-based optimizations and end-to-end integration. Please understand this we have to understand this, that integration back into live frameworks like LLVM has been a very, very hard problem. There are many papers that take the information from the compiler, they predict it, and then they close off the work. But we needed to do more. We have to plug in the information and then make it in the live compiler and make it work and get results. That's the main thing. So, and then this is not just research, but research onto deployment. So this is the entire theme. So with this particular thing, what we want to do is that we want to cover how we tackle the phase ordering problem, followed by loop optimizations, particularly distribution for vectorization and locality. And then primarily we'll focus on some backend optimizations, primarily rationalization and RL for real. And DD will talk about instruction combining, and then performance models and recent LLM based optimizations. So yeah, I'll quickly browse through POSIT-RL. That's the phase ordering of optimizations. What you call this is the classic problem and made beautiful in the LLVM infrastructure, because in earlier compilers, not all permutations were valid, and then they used to give funny results. But current LLVM infrastructure is robust enough that you can tentatively apply any phase ordering. But the question here is that it's well known, one optimization sequence does not guarantee improvement for all programs, point number one, and different permutations may yield different performances. That's all good, both of them are good. So how do you get the best phase ordering? So we built a RL-based framework. For example, it takes the source file as well and converts into LLVM. IR obviously, and then it feeds into the IR2VEC engine, and then IR2VEC embeddings. Once you obtain, then what happens is that you have this is the entire RL framework. It chooses an action, and the reward for the entire infrastructure is standard LLVM MCA throughput given by LLVM MCA. And kind of the and some additional features, like for example size counter, etc., number of instructions and other features. This is used as the reward for this. And so I think the summary is, I think there are a lot more things here, but in summary we report up to around 10% size reduction, and on various architectures, for example x86 and ARC, etc. And yeah, here you are. And there is also execution time improvements, for example up to 10% improvement in time, etc. So that's good. This is for phase ordering problem. Then we tackle one more problem, loop distribution done by our group. You can see the classic loop distribution problem. You have, I mean, this is not indented properly, but what we want to understand is that this particular statement is the blocker for vectorizing this particular loop. So there's a dependence here, and then if on the other hand, if you actually distribute the loop with this guy and each of these having their own loops, you'll have the first guy and the third guy will be highly distributable. That's good. So this is nice. Okay. So this is nice. So for example, we are currently talking about loop distribution being an enabling transformation. It will actually enable vectorization. That's the current focus of the problem. So you have a maximal. This is the classic Alan Kennedy paper. It takes a particular loop and then does something called maximal distribution. You see a loop like this, and then you see a blocker here. For example, there are dependencies here, and then some dependencies here, and then the reduced dependence graph becomes something like this. You have self-dependence here, self-dependence, and then you have a dependence from here to here, S1 to S3. S1 to S3 because of, I believe, A, and you have self-dependencies everywhere. So this is the classic Alan Kennedy framework, reduced dependence graph. And then they propose selecting the constructing the strongly connected components, and then that's it. And then it stops there. It stops there in the sense that it gives a maximal distribution, and we're done with it. But the point is, it turns out that it's not the optimal distribution, and then that's what we want to cover. The overall problem, which is nicely suited for ML, is that there are various topological orderings, and then we want to select one of them based on reinforcement learning, or in general, for example, machine learning. That's the problem which we want to cover. So there's a framework which we built. For example, the input program, we have a pre-distribution passes, and then you have construct the strong linked components dependence graph, and then it is fed to the IR2 engine, which also has the LLVM IR representation as well. And then it goes into GGNN, and then there's topological walk on it. And then there is a nice what to call RL block. You have node selection agent and distribution agent, and then you keep on updating the SDG. And then the reward, reward is some kind of information which is gathered from the each of the passes. For example, it is a subsequence. What happens is that the subsequences of the our particular algorithm doesn't really function on the entire pass sequence, but only selected subsequences that are carefully manually selected. From there, we select the distribution happens. Okay. So there are various results here, up to 5% improvement on execution time, and etc. I think you can. That's one on various, for example, TSVC or various polybench and CNN, Maxpool, etc. So from there we jump to the pretty difficult problem which bothered us for at least a couple of years, bunch of years. We call it reinforcement learning based registral regression. Registral regression is a very classic problem. Registers are scarce, unbounded number of variables and finite set of registers, and one of the classic NP-hard problems. And there are various solutions. Even in LLVM, you have there was a registral locator named PBQP, based on partition Boolean quadratic programming, and a bunch of heuristic approaches. For example, there is a greedy allocator, there is a fast allocator, there is a basic allocator, etc. So the question here is that, I mean, this is well known. You have seen it many times in classic textbooks. You have this particular standard program, and then you have X interferes with Y, Y intersects with Y, Z, and then you have this particular interference graph. And then you can color it in nice manner. How what happens when you color with this coloring happens in various phases. For example, there is a coloring, there is spilling, there is a we'll get to the actions in a minute. So this is the standard coloring. So there are various actions that can happen in a registral locator. You can either split the graph, or you can coalesce the graph, or you can do eviction or spilling. We'll go through that one by one. So for example, splitting is, for example, you can split the particular X into a bunch of duplicates, and then that's a splitting, and then you can have coalescing of various variables that improves the registral location in some sense. And then you have this eviction. You can throw out a variable, and then you can improve the thing in a nice manner. And then you can spill. You can directly, if you mark a node for spilling, then you can get potentially color the rest of the nodes in the graph. Okay, so the question here is that it's important even in a production compiler like LLVM. No, there is no single best allocator, and greedy performs better in general, but that's not guaranteed. And then greedy allocator heuristics are either spilling, coalescing, eviction, spilling, and then PBQP just chooses coalescing and spilling. These are heuristic phases in the entire registral locator. And for this, this builds into a nice framework. So your source code is given into this MIR. MIR is a variant of the LLVM IR of the IR2VEC, and then LLVM IR low end IR. And then from there you construct the MIR2VEC, and then you have these embeddings. These we call as MIR2VEC, and what happens is interference graph is also, this is an entire module is built in our group. You have ML registrator, and then you have the gRPC stub. So it's important to see that there is an LLVM environment and there is an RL framework, and then there is communication between these two stubs using gRPC framework. This is a precursor to what we are going to talk at the end of this talk. We have generalized this using something called a compiler bridge. In general, compilers need to talk to RL frameworks or ML frameworks, and then you need a nice communication mechanism. I'll talk about it at the end of the talk. But here, let's focus that the communication happens only through straightforward gRPC or even, for example, pipes, Unix pipes. So this particular node embeddings which are communicated here, they go through a GGNN and then GGNN, and then there are various actions that happen in the RL framework. There is a node selector agent, and then there are various actions. As of now, the published CC paper, it was last year's compiler construction paper. So in that, it talks about only multi-agent reinforcement learning. Currently, we are working to reduce it to something nicer. But as of now, it has various. It has various actions. For example, you have node selector agent and then task selector agent, and then it takes various actions, for example, splitting, coloring, etc., and then communicates back the information through the gRPC framework to the original program, and then which directly applies the particular color map, and then you get the final register assignment and spelling. Okay, or final decision is relatively straightforward. You have either coloring or spelling. That's the final thing, and then that generates a code. This has been integrated as part of LLVM, and it could generate code for real world codes, including spec all the way. Lot of debugging, lot of real world integration, and then debugging pretty hard. Backend code by the students. That's good. And the global reward function is based on the standard MCA of LLVM. And then the output which is given by the MCA is based on the throughput of the generated function. Very straightforward. And it's binarily it is classified as +10 or -10. That's at a broad level. And then the results are on various spec benchmarks, whether it is spec 6 or spec 17. For example, this is not too easy to read, but what we want to understand is that the baseline is basic allocator, and then the greedy allocator, it gives -51% slowdown, while the RL for real gives -5% slowdown on this particular function from spec benchmark. In a similar manner, for example, you get a virtual picture. This particular function, you have 8% improvement on basic by greedy over basic, and then similarly 28% by improvement by RL for real over basic. So overall, we have you can see that this is a code that works. It has been integrated into LLVM. So let's invite Didi to give the next part.
Okay. Thank you, Ramakrishna, for this introduction. Parts of it may appear difficult because for people who are associated with compilers or deep learning, you have to somehow mesh both these two ideas into something new and something what's happening for the, let's say, roughly last 5 years. There were earlier work, as you may know, on kind of classical machine learning for loop unrolling and inlining and things like that. But whatever, Professor Ramakrishna is talking about is like what's happening over the last 5 years. So maybe some terms getting used, if you're not familiar, we just apologize because we don't have time to explain all the details about, gated graph neural nets and things like that. So, once again, I'll come back to the register problem, register allocation problem, because prior to Professor Ramakrishna's team doing that work called RL for real, me and my team at AMD, we looked at the register allocation problem, but we looked at a much simpler problem. We didn't really want to look at the full LLVM infrastructure, which is much, much harder. Whatever we're trying to do with RL for real is much harder because you have to handle spilling, coalescing, splitting, all this other stuff. So I just started with this basic question that can you do a kind of graph coloring initially using machine learning. So this work is like slightly older, but maybe easier to understand because there are some concepts which are important. So what we tried to do was we kind of said that let's view the graph coloring problem for register allocation as a sequence-to-sequence translation. And when we say sequence-to-sequence translation, it is like I'll give you some vertices of a graph, and you give me the colors on those vertices. So this, and the model will be sitting in between. And the model we chose originally was a bunch of LSTMs. I can show you. So this is for training. On the top, you can see that this was a kind of 3 stacked LSTMs we used for our model. And the input was nothing else but simply the bit pattern of our adjacency vector. So if you look at our adjacency matrix, you take that as an adjacency vector and just input that as your sequence. And the output sequence coming through a dense and a ReLU is just the color of each one of these vertices, okay? So this was a simple sequence-to-sequence problem, and we had this LSTM sitting in between. Now, how do we train them? We actually, at that point of time, trained in using random graphs, okay? We trained up several, 100,000 random graphs at that point, and we said that, okay, now we have trained, what happens during inference time, okay? So what happens during inference time is you now give a new graph, you put all these LSTMs through, and it gives you the colors. But what may happen is, you can't see it here because some of the colors there on the screen is not showing up properly. So there is this thing that happens is not all colors are done properly. There may be cases where because your model is not, it's a probabilistic model, right? It's not fully deterministic. You may get adjacent vertices having the same color. So it's not an appropriate graph coloring. So what we did is we call it, that's why we call it the hybrid kind of an algorithm. We put the initial model first, and then at the end, we put a very fast color collection algorithm, okay? Which is a very fast algorithm. It just looks at the current edge and the surrounding colors and fixes, if there is any edge that we call it as imperfect edge, we correct that color. And that's how we get the proper coloring for that. So this is an example. If you look at this example, if you just, this is a very famous graph that is used for graph coloring called the forest fire graph. And it has a chromatic number of 5. That means you can color it using 5 colors. So when you use the LSTM model, we found that it was coloring it with 4 colors, okay? Which means obviously it is wrong. And there were 2 invalid edges. And those invalid edges were, you can see marked here, between this vertex 3 and 2, and between vertex 5 and 1. So what we could do is like, if you look at vertex 5, right, we could see that we can now reuse one of the colors. So I can reuse actually instead of, both are C2s, right? But C3 is still unused. So I can just color it using C3. But then I come to this, I see that all colors are used up. So I actually have to use an extra color. But at the end of the day, we have got a chromatic number of 5, which is the same as the chromatic number of the graph, and which is following from your model plus your color correction problem, color correction algorithm. So it appeared to be nice. And so we took this algorithm, and we did try to put it in some form in the LLVM, not in this full phase. Once again, as Professor Ramakrishna mentioned, these are the various passes that you can see in a standard LLVM compiler through the interval analysis, spill weight, and all this kind of thing. So really speaking, the current LLVM compiler would not do a graph coloring. It creates the interference graphs, but doesn't do a graph coloring. It takes the interference graphs and then goes through the following steps. So what we did is we captured the interference graph from here, and we pushed it into our LSTM model just to see how the color assignment will take place, okay? And what happens is, what we see is when you do it on the spec benchmarks, it actually shows pretty good results. That is, like if you look at this 557 XZR, spec benchmark, And we see that the LLVM is using 732 colors in total for all the functions. DL before correction was using 500, but all of them are not correct, obviously. Once we correct, we are using 715 colors, so which is like registers rather, much less than what XZ is top. Similarly, for Leela, we see that 961 versus 894. So the middle one is before correction, so which is obviously wrong, and we need to correct it. So what we saw was, using this hybrid algorithm, that is a model sitting in between with a traditional but cheap standard algorithm to correct some of the deficiencies of your original program, you are able to get actually better results than what your current software is providing. So we kind of proposed, this is not in action. If some of you are interested, you can take it up and see whether you can do it. So we propose that we can have a DL-based allocator of this kind sitting in between. We can have the intervals and go through this kind of allocator, and then talk to the current allocator and just figure out which one has a better allocation and choose one or the other. Okay? But this is not, not implemented, just a proposal. Okay, so that's one. So that's looking at same problem, but in a slightly different way and a different part. Obviously, the RL for real did much more solid work on the ground and showed much better results. So I'll also talk about what is called as the NIC, or the Neural Instruction Combiner. As you may know, instruction combining is one of the most used passes and one of the most critical passes of LLVM. And the reason it is like very, very well known is like you get a lot of performance out of this instruction combining. In their paper, I think Zhao et al. Also pointed that it's probably also one of the components where you see the most bugs. Okay? And there's considerable human effort when you move from one hardware to another, building all this instruction combination stuff and all that. So we did a very similar, like we have a fondness for the sequence-to-sequence models. So we kind of said that, okay, can we replace this traditional IC with a machine learned model? And so we kind of thought of three major components. One is an inputter which creates an encoded representation from LLVM IR. We couldn't use IR2VEC at that time because that was still getting developed by Professor Ramakrishna's team, otherwise we would have used it. Then we had a converter, once again, neural network, but this time, though did we use LSTM, we used actually kind of transformer networks by LSTM with attention. And we also had that outputter, but once again, correctness. So as was pointed out earlier, some of these passes that you are doing where it will require transformation, you have to be 100% correct when you are doing the transformation. But because you are running probabilistic models, right, you cannot guarantee that this will give you proper or right code. So if you look at it, our prediction accuracy was only 72%. And so what did we do with that? So let's say this is the training pipeline. Once again, I apologize for the colors. So this is a training pipeline. You can see this here is the traditional instruction combiner. And what we do, we capture the IR before the combiner, and we capture the IR post the combiner. And then we train this NIC inputter from that and create our model. And in the output, because we are getting only 70% correctness, we also need to have a checker tool like Alive. People who are familiar with Alive tool, it's mainly used for checking your LLVM IR for correctness. So you can have to add a checker tool like Alive to see that what you are transformed is actually correct or not. Okay? So just to show what kind of encoding we used, once again, I don't know whether they are visible from the back. Probably we should have used a darker background. Anyway, so if you see that this is a source sequence where you have a sub, you have a div, and you have another sub, and the target sequence for instruction combiner actually converts that div to a shift right. Okay? So a div by 2 is made into a shift right by 1. So this is the instruction combiner, or the maybe kind of a p-fold optimization that has happened. And the table below shows some encoding. We don't need to bother about the encoding right now. But this kind of input-output sequence are fed to this kind of a training system where we have the encoder-decoder LSTMs with attention blocks. We also tried transformers, but more or less performance was really the same. And these were the kind of predicted sequences we got, like, you can see the mul getting converted by shift left, once again mul getting converted by shift left, the whole bunch of ZX mul truncation just becoming one shift left and things like that. So this came really from our transformer model. I mean, not from doing actual heuristics. But there were, as we said, we have 70% accuracy, and there were different types of errors that we saw when we were trying to do this. When we saw opcode mismatch. We saw issues with generating SX and ZX. Also, we saw incorrect constants. So that was one big problem that we faced while doing this, that constants like something like 2 will become something else. And one of the major reasons for people who have done a lot of machine learning is the fact that, as you may know, representing natural numbers or rational numbers or other numbers through an embedding is actually very difficult. Because if you look at a vocabulary in English or French or Hindi or whatever it is, it has roughly a finite number of words, so you can embed it. But if you have natural numbers, it is countably infinite. So it is not easy to embed these sequences. So what happens is when the prediction happens, the embedding may be okay, but your numbers may come out to be wrong. So that's a major challenge you will face in compilers, especially when you are trying to do various predictions, that in your IR, if you have a constant number, maybe it's a loop bound, maybe it's shifting, maybe multiplying by those constants, when you do the embedding and when you actually do the transformation analysis on that, you may have some challenges. So there has been some recent work, which I'm not talking about here, where they tried to do a better embedding for natural numbers. You can just look it up. So that's where things get a bit complicated and you need to be careful. So after talking about these two kind of optimizations, I'll also talk a bit about a cost model. Now, people are always talking in the middle about some cost models where you require the cost model to tell whether I should do certain optimizations, if I'm doing certain optimizations, how I should do it. For example, loop unrolling, very well known, very popular optimization, but how much should I unroll? By factor of 2, by 4, by 8, 16, much larger, not unroll at all. It's all dictated by your hardware, like your number of registers, your cache size, so many other things. Because if you are not managing those hardware well, and you are putting out a wrong loop unrolling factor, you may actually get a degradation instead of an improvement. So what we try to do, and this is a work currently associated very closely with the work I personally do on deep learning accelerators, where we use MLIR. So in LLVM, as you may know, there is this TTI, right, where you can, which is a target transform info, you can go and query TTI and say, okay, tell me for this instruction, what is the cost on this hardware, or okay, shall I get this or that? But if you are in MLIR, though there is some now effort to make something like a TTI, MLIR is at such a high level that if you try to do that, you will probably lose a lot of interesting information. So what was our idea? Our idea was the following, like, I want to predict machine or hardware characteristics from a very high level description of a data flow graph. And this will be via the MLIR. And what I mean by hardware characteristics is the kind of things we looked at were mainly like how much of register usage are you having? Are you going to have register spills? Okay? How much of cache usage you are going to have? Things like that. So here I'm just going to talk about register usage. So let's say people who are familiar, they'll talk about some kind of PyTorch and other graphs that Professor Uday was talking about in the morning. So let's say this is a very simple data flow graph representation of some deep learning operations, right? And usually, for people who are familiar with MLR, we'll probably transform this to some MLR like this on the right-hand side with some broadcast diff. XPU is, let's say, a dialect which is supposed to model your hardware, okay? So this is the MLR on the right-hand side. So the question I'm going to ask this MLR is, I've given you this MLR. Tell me the register usage when I run on platform X. Tell me the amount of cache I'm going to use if I'm running on platform Y. Okay? And can I do it easily? I mean, it's not very easy, but there are some ways. And so what we kind of tended to do was, we once again, as I said, we love sec-to-sec kind of situation. So we wanted to push this entire MLIR as if it is some sequence of tokens, right? Like you do in NLP problems. So I want to look at the entire MLIR as a sequence of tokens. And I could have done similar, like again, IR to VEC, but because this is like an MLIR, not an IR to VEC in LLVM. So we took MLIR, pushed it as a set of tokens. We had our model built. I'll show you what the model looks like. And in addition, we also had some ground truths. So I'm just showing you, an Intel hardware here, but it can be anything. So I actually I run this MLIR on this actual hardware and get the ground truth, and I do the back propagation, and I, converge on that. So that's how, I go on doing these things. So exactly, oh God, oh man, I can't show you here. So anyway, so that's the same code, let's say on the left-hand side. The idea is pretty simple. The idea is I'm going to tokenize everything that you see in MLIR as a sequence. It's like as if it's some English text. Okay, but only thing that they'll have some special meanings, like the adds and the subtracts and whatever will have some special meanings. And I'm just going to encode it all the way through. I'm going to encode my tensor shapes, input tensor shapes, output tensor shapes, and so on. And I'll take this entire sequence as the input, and I'll give it to a model, and I'll ask, tell me the number of register usage from this. Okay, and this is how the kind of model we built. It's actually not really a sec-to-sec. We actually went back to on an older kind of model where earlier, before we used transformers, before we used some of these LSTMs, people used conv1D, not conv2D. They used conv1D with a single dimensional filter running over the sequence, okay? And then do prediction on that. It's almost like saying that it is a cut down version of image convolution for your text. And that's quite popular before all these LSTMs and transformers become popular. And it's actually very fast. So, we can do very fast prediction with that. So we did that. We had the MLIR code. We did the encoding. We had this model. And then what it will finally predict is the register pressure. And we built this model with 6 conv1D layers, some max pool and stuff like that. And interestingly, what we found was our mean square error was within plus minus 5%, which was actually very nice. That is, like, we were predicting the amount of register usage that this very high level MLIR will take when it is brought down to the hardware level to within 5% of the actual number of registers that gets used. Okay? And so this you can see, sorry. This is the predicted versus the actual for one of our deep learning accelerators. I cannot give you all the details for that, but we see that in many cases, close to 20%, we have no diff, which means the actual number of registers used was the actual number we predicted. And there's a difference of 1, difference of 2, so over 3, there is almost no difference. Like, if it's saying that I'm going to use 10 registers, actual usage will be between 7 and 13, okay? So that's the plus minus range that you are going to get. So, so this is a mechanism which we looked at to kind of predict hardware characteristics from a very high level. And my sense is for MLIR and for other very high level dialects, we should not be doing LLVM IR like TTI, because there it is all tied to very low level single instruction latencies, which may not be important when you are looking at a big block defined at a very high level like MLIR and not low level like LLVM. Okay, so how much time do we have? Okay, so this one, I think Professor Ramakrishna alluded to. This is one of the first work which kind of started this journey of people to look at deep learning. Because we talked about, we now talked about IR to VEC, how to embed the IR into the vector space. We talked about loop optimizations, phase ordering. We talked about register allocation. We talked about NIC and ML hardware-driven characteristics. We also want to look at how do you want to do a prediction end-to-end, right? If you want to do some predictions end-to-end. It has flavor similar to the earlier work I've told you, but this is one of the very earlier work, and the thing is the code is pretty simple that you can start using it today. So the question that was raised in this DeepTune paper was, if we have an OpenCL kernel, is that kernel good to run on a CPU or a GPU? It's a very simple question. Should I run it on a CPU? And people will think, why should I run it on a CPU? Because there may be cases where your kernel has a lot of control features and other stuff which may not be good for the GPUs. So how was this problem solved? At that point, there was no IR to VEC, right? So the problem was solved very simply by taking the original OpenCL kernel, then stripping out certain things out of it to create some tokens out of it, and then push it to a model. And then kind of, once again, train it on many OpenCL components and figure out what the answer is. And the model on the left-hand side, you can see is, once again, was an LSTM-based model with some batch norm and a dense. Can I see the code here? Okay. So you can see it was a 2-layer LSTM and with all this kind of things, and the code is here. So this is a pretty simple, straightforward application, which, for example, today, if you are trying to say, okay, I have some code in Python or C, C++, and I want to predict some characteristic of that code for my something else, for my hardware, for some of the other things, how it is suited here or there. You can do a very basic technique. You don't need to do very complex techniques. You can do a very basic technique like this and do a prediction. But the thing is, you should have a fairly large training set to train. And nowadays, you have so much from the Git and other places, so that's not a problem. So yeah, it gave some performance improvement as usual. And then, so obviously, no talk on ML right now can bypass LLMs, right? Because LLM seems to be the savior for everything. And most likely, they will not replace all the great programmers we have. But people are now using LLMs for looking at end-to-end compiler optimization. It's almost like saying that I'll give you a C, C++ code, a Java code, a Python code. LLM will give me the fully optimized code. No questions asked, nothing like looking at each optimization phase, not looking at each correctness, nothing of that sort. End-to-end, one LLM getting pushed, output, we all can go to sleep. Okay? We don't have any work. All of you listening to with bated breath saying that, oh, can I go tomorrow and look at this code? LLM is just behind you. So this is actually, but it is an interesting concept. If you look at today's LLMs, by the way, if you look at, this was actually done at Meta. This work was done at Meta Research, so obviously you'll see Code Llama and all that. You take Code Llama, you give it some LLVM code or some C, C++ code, and ask it like, okay, what does this code look like after optimization for size? And it just gives some gibberish and nonsense output. So like nothing is there. So what happened is this team, they took Llama 2. Llama 2 currently is, by the way, Llama 3.1, Llama 3.2 are already out. So 3.2 for multimodal, 3.1 for normal text. So this is Llama 2. Llama 2 was trained on 2 billion tokens. And what they did was, Code Llama is trained on another 500 billion tokens. They actually added another 540 billion tokens for training using LLVM IR, x86-64 assembly, ARM assembly, NVIDIA CUDA, and all that. Okay? So they did a lot of extra pre-training for that, specifically for LLVM. Specifically for LLVM, teaching it LLVM IR, teaching it things like that. And then they said, okay, let me ask some questions to it. So they tried to work on these 3 particular downstream tasks. One is emulation, one is flag tuning, and other is a decompile. So in the emulation, they will say, okay, I'll tell you the number of passes. Okay, if I apply vectorization, how will the IR look like? If I apply vectorization and loop unrolling and tiling, how will the IR look like? And so if you see here, you may not be able to see because it's all like gibberish here because of the screen, but it says, give the LLVM IR for the following code when optimized using opt minus p. And it gives actually the absolute correct LLVM IR, compressed and saying that I have reduced it from so many instructions to so many instructions. Okay? So if you look for flag tuning once again, once again the prompt was tell me how to optimize this LLVM IR for something, and it will say, okay, you can use the flag A, B, C to run this, and then it will optimize for this. And so on and so forth. For decompilation also, you will actually give them x86 assembly, and it will give you back some form of LLVM IR. So, looks very scary actually. that you are able to do. I'm not saying that this is like the end of the world for compiler engineers, but while we are all sleeping or working or doing whatever, LLMs are learning stuff, okay? LLMs are learning stuff. There is this just a small piece of joke that came as a kind of a meme that while we are busy on our phone, all the LLMs are training themselves, okay? So that's what is happening here. So please be advised that there are some difficult days coming up for all our compiler engineers. So we come to the last phase, and I'll talk for a few minutes before I hand over for the last phase to Professor Ramakrishna again. So all these things that we're talking about, right, we are talking about IR to VEC. So as he said also earlier, that we need to really put it in a working compiler. Otherwise, these are all nice theories. You can talk about it. You can all feel good. But then nothing actually comes about out of it. So there are some efforts. I'm going to talk about one effort, not obviously mine. This came from actually Huawei guys, Amir Ashuri's lab. It's called ACPO. And what they're trying to do in the ACPO is they try to automate two things in this, a loop unroll and a function inlining inside the entire LLVM. So they have an entire built LLVM structure which will do the loop unroll and the function inlining using ML side of things. I'm not going to read everything. This is not very important, the framework, but if you look here, the basic idea is this, that when you are going to do a compile, actually when it goes to your LLVM, the opt passes. In between the opt, you will actually be having an ML pass. The ML pass will collect all your features and apply the autotuner decision and use it for training. And during inference, that same ML pass will actually be calling an ML interface, like he was showing for gRPC and all that. It says run the inference, it will call the inference, it will load the model, run the model, and stuff like that. And the ML models are here, it gets back the result. And this is actually all published code in GitHub. So I just had some code where it shows these are the interfaces that we have. Sorry. These are the interfaces we have to do some of these kind of things, like you can do the run model, you can get the model result, and things like that. And these are the headers, and then you can actually call them for your inlining or unroll and things like that. So this is one usage of how to embed a real ML model into your compiler infrastructure. And for the last part of the talk, which is like another 5 slides, I hand over to Ramakrishna, and then you should all be ready to leave.
So would we. Thank you, Dr. Didi. Okay, we get back to infrastructure. So I think you have seen a lot of algorithms, implementations, and theory as well, and correctness issues with racialization and nice reward models, etc. But in the end, many of you are actually compiler engineers. You would be interested in some kind of what does it mean? How can we build stuff? So the moment you're talking about here, we are talking about one particular infrastructure which we developed recently or good developed recently. It tackles a pretty important problem. The fact that there are various compiler infrastructures that are primarily based on C, C++, and then they have to talk to machine learning models which are primarily written in Python. So you need some way of communication. You need some, for example, whether GCC, LLVM, MLIR, polyhedral comparison, or even, for example, TensorFlow, or Keras, etc. Here you actually see an instance when you have to build communication, and this becomes a M cross N problem. So this has been tackled by various research groups, but actually you can, this is supposed to be bridge here, but you can build a bridge. This is kind of reflects Professor Uday Reddy's talk in the morning when he was talking about M plus N. You can build a single compiler bridge that will take various compilers, and then which allows you to nicely interface with various Python models, model infrastructure, for example, whether it is PyTorch, TensorFlow, etc. So what is the necessity for this? Typical ML compiler instruction is you take the input program, you send it to compiler, and it has to interact with a ML model, and then optimization query, and then you have to serialize the input. You have to serialize the information which you have to do, and it goes into optimization query, and then it goes through training or inference, and then back, and then you get the output. And this is for just for optimization one, and optimization and all the way, and then you may have to iterate back and forth until that particular optimization converges, and then you do this for various optimizations. So this is the typical flow that happens for there's supposed to be an arrow here, that's okay, but this similarly for various optimizations. So the current approaches, most of the current approaches, there is no standard approach. They just use Python wrappers or compiler flags to communicate, and then there is no deeper integration. For example, something as hard and as difficult as racial allocation, you really need a deeper integration. Some kind of superficial communication will not help the work. And then the models are written with C++ APIs, and then there are issues with all of these approaches. So our group built this compiler bridge. So you have these various compilers, you have the data in, data out, and then there is various ML models, PyTorch, Keras, TensorFlow, JAX, and this ML compiler bridge stands in the middle of this. You can choose the various serializations, various ML model runners, and then in a streamlined fashion, you can within couple of lines of code, you can actually plug your optimization with the nice with the correct ML model. That's the main premise for this particular work. This was accepted in this year's CC, and from here. You want to see this? Okay. We're almost done. Where are we heading? The point is that there are end-to-end compiler tool chain there is long way to go, and optimization decisions they should be aided by ML models, and reverse is also true. ML models replace heuristics, hopefully. And these are preliminary efforts, but while at the same time we are happy to say that IR2VEC, which our group developed, is close to being accepted into the LLVM compiler, and Bridge has also received some amount of traction, and so this is code that works and has been used by industry and research as well. So, and we have open sourced our entire infrastructures, IR2VEC, MIR2VEC, Bridge, RL4L, etc. And then they work on various LLVM and other things. So this is based on various references, and that's it. So before we close on, I think it's important to talk about various openings. This is our colleague, Professor Jyoti Vedrada. She has a position for JRF. You may please look at it. I should have written it there. And then we have various research internship and other positions. This is small advertisement. Pardon me for this. That's it. Okay. So thank you. We are open for questions.
Thanks for an excellent talk. We have time for a few questions.
Thanks for the talk, professors. I have a question for Professor Ramakrishna. So he was talking about some of the compiler problems that you were solving using machine learning, namely phase ordering, loop distribution, and rest allocation. And he talked about some of the performance and the code size improvement on the popular benchmarks such as spec. Yeah. Can you talk about the accuracy of this transformation on these benchmarks?
That's a very good question. Like accuracy, did you mean to say the correctness of the transformation, or the accuracy of the, because these are RL based techniques. They converge to the optimality. For example, when we are talking about racial allocation, we compared with greedy allocator. So the accuracy is there in itself, or did you mean something else?
No, I meant once there is a single pass of this machine learning model on a particular code, the output, is it correct. It does produce the same output as the
Yeah,
unoptimized.
yeah. So I think RL by design will be correct because you can encode the constraints. Like when you are expanding your search space, the ones which are incorrect, you are not going to expand.
Yeah, thank
Okay,
you.
so RL, yeah, by design, RL will be, not have correctness issues.
Correct by construction. That's
I had a two-part question on the IR to Beck. So the first thing is you talked about learning some embeddings, right? So what is the criteria for learning the embeddings, right? So that maybe I missed it, or so how do you decide what is a good embedding for your IR tokens, right? And the second part is, in some of your optimizations, you took those embeddings and you fed it to a GNN, right? So if you have already learned the embeddings using data flow propagation, what is the GNN doing in additional?
See, the thing is that you have to get some pattern. We are not in the feature-based world. We have to learn from the representation learning, and to learn the representation, we have to study some quote-unquote real-world programs, and these real-world quote-unquote real-world programs turn out to be spec benchmarks. From then, this is what we call as there are two phases to it. First part is the seed, what we call seed embedding. This is kind of the vocabulary for the entire thing. And then actually the training happens on the entire spec benchmarks. That's good, but that is still not sufficient. That's still not sufficient for the particular problem. What happens is that you have to, for example, for racialization, you have to formulate in a particular manner. You have to create various agents and then the reinforcement learning takes over. So that's so reinforcement learning has its own rules.
So the embeddings are optimization specific, is it?
Yes and no. Yes and no. See, our embeddings they encode quite an important information of the program, point number one, and they can be fine-tuned for the particular optimization. That's the main point which we want to take back.
Thank you.
You want to add something?
Hey, thanks, Dibyendu and your is here, Mahisha here. So this is a pleasure to listen to you guys. Just a quick question, rather two questions. We used to have this profile-based optimization once upon a time, right? Maybe it is still there in compiler era. So how much of the gains that you see here are better than what you could achieve with profile-based optimization in that other world, right? And second one is there a significant impact on the compile time due to all this inferencing and all that?
Dr. Didi will give a better answer, but let me just say that the RL for real plus plus is, we are working on it, and we are working on profile based, applying RL for real for using the profile on the profile code. That's it. So that also.
Yeah, so first part is, I think none of these are like, we have not worked with profile stuff. So I doubt, if you apply similar techniques on profile, it will improve similar manner. That's my take. We haven't tried that. And the second question is much more important in the sense that, we say that we're going to deploy a model while compiling, and that inference has a cost. And the more complex the model is, the higher time it will take. And actually, we have not deployed certain things, though it looks very good on paper, because the round trip for that inference is actually high. So that's a valid point, but it depends on the situation you want to optimize for. And then if you have infinite amount of time to optimize, but as long as you get very great code, you can take that hit. So, but it's actually a nice question, because that's a choice, because let's say you are in a JIT mode and you want to do this kind of model-based inference. If your model is very heavy, your JIT time will blow.
Hi, amazing presentation. So what I wanted to ask, you presented about machine learning optimizations on the IR, which will eventually get converted to an ELF file at the end of the day. And ACPO, like you mentioned, is already using it. So what I wanted to ask is, when we are not using machine learning or any kind of intelligence to optimize the IR, we are doing it in a very algorithmic manner, and we can keep track of which we can keep track of debug symbols, which debug symbols associate with which part of the ELF file. But when we do it using machine learning, is it still possible to do that, or we lose this association with debug symbols altogether with the resultant binary?
Yeah, tricky question. See, Mahisha is here, so we used to work together in HP long back, and our manager who was in Cupertino, she had written a paper on debugging of optimized code. So it's a very old paper if you look for Michel Rosetta and debugging for optimized code. Debugging for optimized code is always tricky, like especially if you go to O2, O3 interprocedural optimizations, it always gets trickier and trickier to, as you were saying, to maintain the one-to-one correspondence between your, in optimization, the actual debug symbols. So definitely here, with the IR happening, you will see similar problems. Now, whether we can resurrect some of it back, I don't think, probably it's a new space where you can work on, because I haven't seen any work which says that recover debug symbols for optimized code using ML. But it will be a problem, it will be a problem like in debugging for optimized code.
Will LLMs be able to generate code for hardware which is new, like new hardware features?
Okay, that's another toughie. See, this almost like when the new, if you see the new LLMs coming out, people do not even fine tuning; they are doing few shot learning. Okay. So what is few shot learning? If you know already, like it's already run and pre-trained on so many billions and millions, trillions of tokens. Maybe you give some 5 examples of what you want, right? And it learns from that 5 examples and all its previous knowledge. So that's what people are trying to do. They even do one shot, just one example, right? And just do a one shot learning over that LLM. So if you have a totally new architecture, let's say if you can get 10 examples, we need to see whether it works or not. But that's what is being used in the NLP space and these other spaces today. They are doing, like it's trained, now you have a totally different area on which you have, probably no training set has been done on that. You give a few shot learning on that and you try to see how it does. So that's probably what can be done on that. Otherwise you have to do a fine tuning again. You have to get at least 1,000, 2,000 examples, fine tune it, have the original one and redo it.